Okay, so my name is Alban Farchi. I'm a researcher at CEREA in École des Ponts. And today I will present you our collaboration with ECMWF on the topic of model error correction with both data assimilation and machine learning. So I will start this presentation by a short methodological introduction. And then I will show you a numerical illustration with a 2D QG model. So let us start from this typical supervised machine learning problem. Given observations Y of a system, we want to derive a surrogate model of that system. The surrogate model depends on a set of coefficients P. For example, these could be the weights and biases of a neural network. And the optimal set of coefficients are those to minimize this cost function. Obviously, this formulation requires dense and perfect observations of the system, whereas in numerical weather predictions, observations are usually sparse and noisy, which is why we need data assimilation. So a rigorous way to include data assimilation in our problem would be to derive a new cost functions, which now depends on both model parameters and the model trajectory. This cost function is looks like a typical weak-constraint 4-DEVA cost functions, where you have a first term, which is the departure to the observations, and the second term, which corresponds to the model error term. Now, how are we going to minimize this cost function? So the idea here is that we can use data assimilation to estimate the state of the system, and we can use machine learning to estimate the surrogate model. And what we will do is we will alternate data assimilation steps with machine learning steps in a way which mimics a sort of coordinate descent. So now back to NWP. Even though numerical weather prediction models are not perfect, they are already quite good. So instead of building a surrogate model from scratch, we could use this combined DA-ML framework in order to build a hybrid surrogate model where we have a physical part and a statistical part. And in fact, the statistical part would be trained to learn the error of the physical model. So the general idea is that model error correction is an easier inference problem than full model emulation, meaning that we could use smaller neural networks on less training data for this problem. So, but before we introduce the model error correction, we need to discuss a bit about the typical architecture for the physical model. So typically, a model will be defined by a set of differential equations, which define what we call the tendencies, equation 1. These tendencies will be integrated from time t to time t plus delta t using a numerical scheme. And then we compose several integration steps in order to define what we call the resolvent from one time step to the next. And then we can apply a correction term either as an integrated correction from one time step to the next, that would be in the resolvent, equation 3, or we can directly correct the differential equation. So that would be a correction in the tendencies, equation 1. So we have these two possibilities. So let's say we are going to the resolvent correction. So one possibility for the hybrid model could be to use an additive correction. So in this case, the hybrid surrogate model would be defined as the sum of the physical model, the original one, plus the statistical model correction. What is really important here is that the contributions of the physical and statistical model are totally independent. And therefore, the statistical model has to predict the relationship between the state and this quantity, which happens to be the error of the physical model. Now, if we go for the tendency correction, then in this case, the physical model and the correction are entangled, which means that we need the tangent linear of the physical model just to train the correction. And in fact, this is much more technical. And this is why for this study, we are going for the resolvent correction approach. So now we arrive to the second part of my presentation, which is dedicated to the numerical illustration. So I will start by briefly showing you, by briefly describing the QG model. So this model expresses the conservation of potential vorticity for 2 layers of constant potential temperature in a 2D plane. So the potential vorticity is related to the stream function using these 2 equations, one for each layer. We take a periodic domain in the x direction, and we take fixed boundary condition in the y direction. And we use 40 times 20 grid points for the discretization. And what you see here at the bottom of the slide, it is a typical snapshot of the stream function, but only for the bottom layer. So this is our true QG model. And what we now will be doing is we will add some model error on top of this true QG model in order to build the physical model. So the physical model will be a perturbed QG model, and our goal will be to recover the true model using only observations. So what are we going to do for the perturbation? We are perturbing the layer depths, we are changing the integration time steps, and we are changing the orography constant. So you have all the values for the true model and for the physical model, which is a perturbed one. So now we have our true model. The true model will be used to generate sparse and noisy observations. And what we first need to do is we need to do data assimilation with the non-corrected model. So for the data assimilation step, we assume that the control vector will be the stream function, which gives us a number of variables equal to 40 times 20 times 2 layers is equal to 1,600. We will take observations every 2 hours at 50 random location. And we will use an observation standard deviation of 0.1, which in this case represents 2% of the model variability. For the data assimilation step, we will use a 4-divar algorithm, and we will take consecutive windows of 1 day. And in order to yield the lowest analysis root mean square error, we will optimally tune the background error covariance matrix, which is 1 parameter of the 4-divar algorithm. So we have applied this method for 1,000 consecutive assimilation windows. We have observed that the analysis root mean square error stabilizes after about 5 windows, which is why for the machine learning dataset, we will drop the first 8 windows for safety. And then the time average analysis root mean square error we obtain is about 0.24, which corresponds to 5% of the model variability. So obviously, this is something that could be improved. So now it's time to do the machine learning step. So if we had dense and noiseless observations, our inference problem would be to predict the relationship between the true state and this quantity, which is the true model error. So however, with sparse and noisy observations, our best approximation of the truth is the analysis after the data assimilation step. So we replace the truth here, here, and here by the analysis, and we get a new inference problem, which is to predict the relationship between the analysis and this new quantity, which is the analysis increment. So the idea of using analysis increments in order to infer model error is not new in the data assimilation community, but what is new here is the use of neural networks to that end. So that's exactly what we have done. We have used the analysis and the analysis increments in order to train a collection of neural networks. And what I will show you on this slide is one training example. So we take a simple dense neural network, which has only fully connected layers, linear activation functions, and the number of parameters is about 14,000. So we train the model using the analysis and the analysis increments. We train for 1,000 epochs, and then we compute the normalized test mean square error. And we obtain about to the analysis dataset. But once we are there, we must remember that our goal is not to predict the analysis increments, but the final goal is to predict the model error. So in order to evaluate our ability to predict model error, we recompute the test mean square error using the truth dataset, and then we obtain a test mean square error of about 70%. So to illustrate this difference, we show here 2 snapshots. On the left, you have a snapshot of true model error, and on the right, you have the corresponding neural network prediction. So what you see overall is that visually speaking, the neural network is able to predict correct model error patterns. So you have this red pattern, this blue pattern here. But what is really a struggle for the neural network is to predict the correct model error scaling. Okay, so we are here, we have trained our neural network, and now what we want to do next is to plug in the neural network and the physical model in order to obtain the hybrid model. And we want to evaluate the ability of the hybrid model to do forecast and later data assimilation experiments. So we start with the forecast experiments, and what we compute here is the forecast skill of the hybrid model. So the forecast skill is defined as root mean square error after a fixed lead time starting from the correct initial condition. So you have in blue the forecast skill of the physical model without the correction, and you have in red the forecast skill of the hybrid surrogate model. And finally, you have in the black dashed line is the model variability. So what is really satisfying here is that we have a hybrid model which is more accurate than the physical model, and we have a correction which is effective until 10 to 15 days of forecast. So we are very happy with that, but there is still more to experiment. And in particular, we want to show the difference between all the collection of neural network we have trained. So of course, I won't show you all the forecast skill of the individual neural networks, but what I will show you here is the root mean square error at day 8, so after 8 days of prediction, as a function of the length of the training data set. And we have here each time the best of 2 categories of neural network. So in blue, this is the best of the linear neural networks that we have trained. And in red, this is the best of the non-linear neural networks we have trained. Non-linear neural network, which uses the rectified linear unit activation function. So what we see from this plot is that it is possible to train effective corrections using only short trajectories. So we need less than 100 snapshots of analysis in order to get effective corrections. Furthermore, we see that nonlinear neural networks noticeably outperform linear ones, which is a sign that nonlinearity plays a role in our inference problem. And furthermore, this is not shown by this plot, but we have found that fully connected layers can be, to some extent, replaced by convolutional layers, which are more scalable to high-dimensional systems. So this concludes this first part for the forecast experiment. And now we want to evaluate the ability of the hybrid model in data assimilation experiments. So the problem with such experiment is that we have observations that are available every 2 hours, but the machine learning, the neural network predicts the error for a 24-hour integration. So in order to circumvent this issue, we need to make an assumption. And the assumption we will make here is that we assume that model error grow linearly in time. And more specifically, what we will do is we will take a model integration for a single time step, which is this one. So you have the first term, which is the original, the physical contribution. And you have the second term, which is the statistical correction, the neural network correction, rescaled by a factor, which is the ratio between the integration time step and the data assimilation window length of 24 hours. So this is what we have implemented. We have put that in a 4-diva algorithm, and we have performed an experiment using exactly the same setup as previously. And we have reported here the results of that experiment. You have here the analysis root mean square error when using the physical model as forecast model, so the 0.24 value as previously. And you have the analysis root mean square error when using the hybrid model instead of the physical model, which is now 0.18. So this is very satisfying because we get, in the end, a 25% reduction in the analysis root mean square error. However, this is not yet the same level of accuracy we could obtain with a true model. And we wanted to know if it would be possible to further improve the analysis. So we have experimented a bit, and what we found out is that the main limitation, the main limiting factor, is not the accuracy of the model error prediction, but it is the assumption of linear error growth this time. So you have here an illustration of the model error starting from the same initial condition, but for increasing lead time. So for 1 hour, so this would be the short time model error, and for 24 hours and 48 hours. So both have been rescaled by a factor 24 and 48 in this case. So these are very different from one another. So what we conclude is that if we want to further improve the analysis, what we really need to correct is we need to correct the short-term model error. And if we stick to the resolvent corrections that we have been using so far, this is a challenge because it is much harder to detect the short-term model error in the analysis increment than it is to detect the, say, mid-term or long-term model error. So therefore, the most natural way to do it would be to go for the tendency correction instead of staying with the resolvent correction. And this will be the topic of our next study. And this concludes this first presentation. Thank you for your attention.